All right, last talk of the day, certainly not least. I'll be loading it up and Martin will MC.
So before we move on to the poster session tonight, which will be in the open area downstairs, by the way, we have a very exciting last talk by Armand Joulin from Facebook AI Research in New York at the moment. Armand obtained his master's from the other École Polytechnique, the one in France, not the one here, and then got his PhD from ENS in computer vision in Paris. So then after spending a postdoc also working on vision, he then moved on to Facebook, where he changed the topic and is now mostly working on text and other interesting aspects of AI, and very happy to have him here today.
Thank you, Martin, for the nice introduction, and thank you for inviting me to talk here. I first wanted to talk how you can scale machine learning for general text understanding and computer vision, that is like language modeling, image classification and text classification, but I thought for the diverse crowd that we have here, it would be maybe better to focus on only one of these subjects for most of my talk, and then at the end maybe talk a little bit about the rest. So I decided to focus mostly on text classification because it is a problem that is core of many applications, information retrieval, web search, sentiment analysis, and so on. Usually when you have a pipeline that requires a text classifier, you have three important components that are needed. First, usually when you don't have a lot of data to train on, you need to pre-train your text representation. This is usually done by Word2Vec or a similar model. Then, if on the other end of the spectrum, you have a very large amount of data, you need methods which are extremely fast because you cannot wait for days before you have your numbers. And in the end, for a lot of applications, you may want to have models that have very small memory footprint. If you want it to run on mobile device, on robots, or others. All of these problems, we have been trying to address them in papers as well as in a library called FastText that we have open sourced a few months ago. And I'm going to go over how we answered all of these questions in the following talk. So first, the common way of doing text representation in an unsupervised way, or at least the one that is the most popular right now, is actually to do word representation. So the idea is to represent words by a continuous vector, and generally the signal you use to train them is to predict their context. This idea is very old, it's from the 50s, but has been becoming very popular recently thanks to the work of my colleagues at Google, which was run Word2Vec. I'll briefly go over what is exactly doing Word2Vec. It's actually very simple. All it does is that it computes a score between a word and its context. Usually the context is the word surrounding that word. And all you do to do that usually is you just take a dot product between the two and you minimize some loss on top of that. This works extremely well in practice, even for pre-train to pre-train text embeddings. However, this ignores completely the structures of the words. And while that might be fine for English, for a lot of languages, this is going to cause a lot of problems. So what we propose as an extension of this work is to basically decompose a word in all the possible character n-grams you have, from usually a size of 3 to 6 n-grams. For example, if you take a very popular activity here, skiing, you can cut it into ski, ski-e, keying, and so on. Then what you do is you just represent the word by this bag of n-grams, plus an embedding for the word. This is very simple. It is very simple to code and also very fast to implement and works surprisingly well. there is a few technical details that are important to make it work well, that I'm going to review very quickly. First, as I said, you take n-grams between 3 and 6 characters. You usually use something called the hashing tricks, which is basically a way to transform strings into a hashing function that helps control your memory footprint. And then you train it with stochastic gradient descent and a parallelizable algorithm called OGWIDE. Even though we compute way more things, we are only 2 times slower than Word2Vec at training time. In terms of performance, if we look over a variety of languages and compare to the standard Word2Vec, there's 2 models in Word2Vec. There's Scapegram and SIBO. Here we see that on most of the languages we outperform Word2Vec. At maybe the exception of English, but that's not very surprising because words are less composed. You compose them less. We are not the only one who have been working on this problem of how to do word representation for many languages. And people usually use more complex model. And again, we outperform the previous state-of-the-art by usually a pretty large margin, around 10% or something. And our code, again, works way faster than what was done before. So this is for the pre-training. It is relatively simple. It could be considered as an extension of Word2Vec and can be used when you want to train on small amount of data text classifier. When you want to train on a large corpus, you may also want to have a very fast text classifier. So a lot of the state-of-the-art right now is based on deep learning, usually convolutional network or highway network, like ResNet. Unfortunately, these models are usually very slow to train. On the other hand, we use a very simple and known way to represent text, which is simply to take bags of words and n-grams. And then we just train a softmax on top of it with the additional trick of having a rank constraint or a matrix factorization here. That is very important because if you have a lot of classes and a lot of words, if you just train a linear model, you are going to have a huge matrix that is very hard to optimize. If you just use this trick, then your model is quite small and very easy to train. Again, there's a few tricks that are extremely important to speed everything up and achieve a state-of-the-art performance. The first is, again, to use a feature hashing, which was also used in a library called Vopal-Vabit. You also need to use an approximation of the softmax when you have a very large output space. That has been proposed by Goodman in 2001. Our implementation is quite different, but the idea is basically there. You can also use, of course, pre-trained vectors, and as for word representation, we still use SGD plus OGWIDE. Here is a comparison on the small output space of our model compared to state-of-the-art. So in terms of performance, so Zheng et al. is a convolutional neural network on characters, and Kono et al. Is a ResNet on text. We achieve better performance than simple character-based CNNs, and we are slightly below ResNet. However, in terms of training time, this model takes several hours. This is the time per epoch, so like it gets up to a day per epoch. So usually you have to run them for 10 epochs, so it's 10 days. And for the ResNet one, it usually takes around a day also to train. For us, it takes in the order of a few seconds. And you get basically the same performance. Now you can, and one other thing is that we can also move to large output space, while these other models cannot. Here, for example, we are training over 100 million documents with a labeled space of more than 300,000 classes. So there is very little methods that can scale to there. One of them is tagspace, which is an extension of a previous method proposed by Google called Wasabi. And basically, if we compare to this method, we achieve a gain of around 10% while being way faster. They basically train in something in the order of 5 hours, where we take 30 minutes, and we can test also in like way less time than they do. So far I've presented a method where you can achieve state-of-the-art classifier which are extremely efficient. However, they have a huge drawback. Like any linear model, they usually requires a lot of memory. Each word needs to have its own embedding, each class needs to have its own embedding, and so usually you have to store tons of data. This is great when you want to run it on a cluster or on a laptop, but nowadays a lot of device doesn't have that much memory. And especially if you have something which is that fast, you may want to put it on a mobile or to put it on a robot. So we basically tried to compress these models in order to do that. So just for an example, on a small output space, a fast text model takes around 100 megabytes. That's quite huge. And if you're on a large data set, it gets up to 12 gigabytes. So how do we compress this type of models? We applied 2 ideas. The first one is to use quantization approaches, which are usually designed for retrieval, but use them for compression. And the second one is simply to prune the dictionary, so the words you have, based on the norm of their embeddings. All this put together leads to a compression of 100 to 1000 with almost no drop of performance or speed. So let me first explain what type of quantization method we use. So we use a method called product quantizer, which was introduced by Hervé Gégou in 2011, and where the idea is quite simple. You take your vectors and you split them in different segments. And on each of these segments, you're going to run k-min. If you properly tune your parameters for k-min and the number of segments, you can get a pretty big compression already. For example, if your vector is of dimension d, and you take d divided by 2 segments and 2 to the power 8 centroids, you already have a compression of 8. So why 2 to the power 8? It's because then you can store the codes on a integer 8, uint 8. So that's already pretty good. Also, one nice thing is that it's very simple. It's just a bunch of k-mins that you have to run. And k-min is very easy to parallelize. So it's very simple to implement, and it's very fast. Another nice thing about it is that at test time, to reconstruct a vector, you just have to look at all the centroids and just add them together to reconstruct your vector. So you basically only have a constant factor and no additional complexity. So and the constant factor is around 2. That's what we observed. Again, there is a few tricks that you need to have in order to really make that work. The first one is that norm and vectors has to be quantized separately, and this is very, very important. The reason is that the norm of the vectors contains how important is a word, because our model train, the way your model is trained is puts all the weights to the word embedding. So if a word embedding a very high norm, it means that it's very important for the classifier. So if you remove that information, or if you destroy a little bit that information, your classifier is going to be way worse. So that's why we observe that basically just quantizing the norm separately was working way better. Also, we used a strategy that I think could be also extended to deeper neural network, which is what we call bottom-up compression. Basically, you start from the lower level and you compress as you go up. So for us, it's just the embedding and then the classifier. But we have run since then a few experiments, and we have seen that for deeper network, this is actually a good strategy to quantize all deep model. You can also retrain the layers as you go up. That improves your performance, but it's quite costly, so I wouldn't recommend it if you just want to have something fast. But it is still important. So here is a few examples of like how good are the quantizer compared to standard other quantizer that has been proposed in the past. So you have LSH, which is in green, PQ, which is the one we have taken inspiration of, OPQ, which is an improvement over it, which is way slower, but usually gets better performance. And there is the one we use, which is, this one, which is basically PQ with the norm put it on the side. As you see, here it's how much we compress. So the more on the left you are, the more you compress. And the black line here is the model, the full model. So as you can see, if you use PQ or OPQ, as long as you separate the norm, you can compress pretty well without losing any anything in performance. While if you use LSH, even if you put the norm on the side, you directly have a loss of performance. So the second strategy is feature selection. So we could have done that using sparsity inducing norm, but we wanted something that you can run when your model has been trained. And what we observe is that you could do that simply by trying to find a sparse model which were close to your model under coverage constraint. What I mean by that is that if you just try to find a sparser model, you're just going to take the k larger embeddings. But if you do that, you may not have you may have lost a lot of in your training set. You may have examples where none of these words are going to appear, and so you are never going to be able to classify them. So this problem is NPR'd, and there's a lot of literature on that. So we just use a very greedy approach to it, which basically is to run over our documents and always pick the word which has the largest norm and which is not in our set. And that works very well in practice. So here is an example of how pruning works in terms of compression. In red, we have put, we see character-based CNNs. These models are very interesting when you want very small memory footprints, because when you have a character-based CNN, there is no word embedding. So you just have like a few fixed number of inputs, and then all the memory is just in the layers. And since they are convolution, usually they are not very big. As you can see, as we decrease as we prune, like the blue line is the more you go on the left, the more you prune. You see that you can prune quite a lot without losing any performance. Note that everything is in log scale. So the point here is 100 kilobytes, while we started from a model which is usually around 100 megabytes. And you see that you basically have like almost all the time no loss of performance, and you are basically achieving a compression rate of 1,000. You can even go to the extreme and try to fit it on very, very small memory. And you have to tune a bit the parameters and so on in order to do that. But if you do that, you basically have only an average difference in performance that is less than 1%, and basically you get a very, very small model. So this could be useful for any computer or things that has almost no memory. Or if, for example, you want to run a lot of them in your mobile phone, like because usually you may want to have a lot of text classifier, not just one to predict sentiment analysis, one to predict tags, and so on. And so each of them should take very small memory. So in summary, here, I've presented like very simple linear models, and I've shown that they are actually they obtain basically state-of-the-art performance on text classification, and they are extremely fast. And if you use a set of known compression techniques and a bit of tricks on top of them, you can also make them extremely small, and that with almost no cost of accuracy or speed. The code for all that, but the compression is available online. The compression should be available in the coming weeks. So there is a few directions we want to take to improve that. So the first bullet point that is missing is that, as I said at the beginning, right now we are working on word representation. And I think that this is not the right way if at the end your goal is to have text representation. We should find ways to have better text representation right away and find signal to learn them on extremely large data sets. The second one is that we use very simple algorithm to parallelize. We still have our model is extremely fast, but I think you can go even faster, and you can scale to even bigger data set in the same time. Also, as I mentioned, right now we are compressing existing model because we think that in practice this is good enough. But all the evidence we've seen while we were exploring that is that we could actually do it during training with sparsity-inducing norms. And these norms, this should help us to basically compress and train at the same time with almost no loss of time, of speed or accuracy. So this is an ongoing project that we are also working on. And finally, we are also trying now to add visual features to this. And the problem that we have right now is that visual features, like we have usually, are computed with ResNet or things like that. So if you have pre-trained vectors or pre-trained features and you just add them to that, we can go fast already. But the problem is that we don't think it's a good thing to run first ResNet and then save the features and add them to a text classifier. What we hope to get is like very fast approximation of models like ResNet, and we think that to do that we should revisit all the work in efficient features like surf or others. Also, I would like to mention a little bit why I think it's very important to move to a faster CNN. The thing is, we hear a lot, oh, ImageNet is really impressive because you train a ResNet on this data set and you can transfer it everywhere. And that's true for a lot of problems. It's really impressive. But the problem is now ImageNet is basically solved. Like ResNet is at 3%, I think, of error now, and we basically get to the same level of error as MNIST or CIFAR. So if you want to now build better features and so on, you need to move to new data sets, and we don't really have a bigger data set which is annotated. So if we want to basically go a step further in computer vision and object classification, which I think is not solved, even though ImageNet might be solved, is to move to unannotated data sets like Flickr here, where they released 100 million images. And as you can see, these images, like this is really taken randomly, doesn't have the same distribution as the ImageNet dataset. And the text that comes with it is way more noisy and doesn't have the same property as the ImageNet one. So I think that if we want to now move to better model, we should move to this type of data set. And the problem is that on this data set, current approach are way too slow. For example, we train AlexNet on this data set, so 100 million images with 4 high-end GPUs, and it takes weeks to obtain performance. And this is good if you have to do it once, but if you want to do research, this is not good because you have to wait like weeks basically to improve your model, change parameters and so on, or have a massive GPU farm. But the good thing is that even by taking an architecture that has been designed for ImageNet and taking optimization scheme that has been designed for ImageNet, when you use more data, even though they are noisy, you can get performance which are improving over the one you get with ImageNet. Like here, for example, we transfer to Pascal, and we see that model trained on 100 million images achieve slightly better performance than the one trained on ImageNet. So in order to achieve that, we needed to add a few tricks of optimization, obviously, because here we don't have 1,000 classes. We took 100,000 tags. And so we needed to make some approximation to the classifier. But we think that this is a proof of concept that going to this data is promising even if you want to transfer later on. Another one that I want to quickly go over is a more recent work we did also with the same philosophy that instead of going on a small data set with a very powerful model, let's go to a way bigger data set with a not so good model. For this problem, what we did is we looked at caption problem, and instead of using very good language models such as LSTM, we decided to replace them by very old, poor n-gram model such as the Jelinek and Mercer one. The advantage of these models is that they basically cost you nothing on top of the CNN, while LSTM needs to basically go over all the sentence and so on, and is quite slow. What we observe is that by doing such a strategy, training them on a gigantic corpus of caption, which are not the typical caption you see in annotated dataset. There is no cat on the sofa or something. They are usually of that form. So kind of, sometimes they are good, like plain approaching, but most of the time they are not so good. And fine-tuning the linear layer to match the distribution of the typical dataset that people use for captioning, we are able to achieve better performance than language model-based captioning system. We are not as good, of course, than model that has been designed for caption retrieval. This is a caption retrieval task, but compared to the one that are using more complex language model, we are actually able to achieve better performance. And that's it. Thank you.
Thanks very much, Armand. Any questions?
So you have told that the models, the very shallow model of fast text has the state-of-art performance, and it has no disadvantages we would expect of usual deep learning models. It's small, it's fast. So what good is deep learning, CNN-based work, which was done in NLP classification problem? Are there any advantages to it?
That's a great question. So I don't claim that we have this is the end of the story. As the results show, ResNet actually achieve better performance than we do, like around 1 to 2% better. It is still significant. So I think they're capturing more statistics than what we do. My feeling is that the advantage of a CNN is that you don't have to really care about the statistics you are going to capture. You just throw that, it's end-to-end, it's very nice. So you're going to get good performance with minimal effort. If you want to design something as we do, you need to look a little bit closer to the statistics and so on. So what we did with FastText is we basically built that in one thing that you can right away use. But if now we want to match the performance of ResNet, we are going to have to try to add new statistics. And we are going to have to do it by hand, basically. So there is pros and cons in both. I wouldn't say that this is the end of character-based CNN, but it shows that if you at least care about speed, they are probably not the way to go.
Any other questions? No? All right, thanks very much again. Okay, well, this concludes the sessions for today. So again, as a reminder, we have official poster sessions now. And then at 7, we open doors at the Casino Montbenon. The link is also on the website. And again, as a reminder, tomorrow morning we start at the same time. Definitely don't want to miss the first session, of course, on purpose. We put very nice speakers there. I mean, obviously all the speakers are very good. But I just want to highlight again that we have Nuria Oliver tomorrow, who's the chief data scientist at Vodafone, was many years at Telefonica, and also runs the CTO of the Data Pop Alliance now. So this is going to be a great talk. And then, of course, Emmanuel Mogenet, the head of Google Research Europe, which is now the largest research group of Google outside of the US, and quite possibly the largest machine learning research group in Europe at the moment. So that's tomorrow, but I hope, of course, to see you all tonight at 7 in Montbenon. Thank you. I have a meeting with Google at 6.